Hello, in this second talk I will explain how to extend Lawson's technique into homogeneous three-manifolds with a symmetry group of dimension 4. These spaces, I will assume always that they are simply connected, form a two-parameter family of examples, the so-called E kappa tau spaces with kappa and tau two real numbers, or also called the Bianchi-Cartan-Brantzianum spaces. So this is a nice way of summarizing all these spaces. When tau is equal to 0, we get the product spaces S2 cross R for positive kappa, R3 for 0 kappa, and H2 cross R for negative kappa. And when tau is different from 0, we get the Berger spheres, the Heisenberg group, and also the universal cover of the special linear group of matrices of order 2 with real entries, with some left invariant metrics. So this was very popular in the last decades because they give a common framework for Thurston geometries except for the hyperbolic space H3 and the group Sol3. In fact, E kappa tau admits a very particular structure because it has a unit Killing vector field. So, by projecting in the direction of the integral curves of this unit Killing vector field, we get what we call a Killing submersion structure. This means that there is a Riemannian submersion from E kappa tau into the surface M2 kappa of constant curvature kappa, whose fibers are the integral curves of the Killing vector field. In this case, there are very well-defined notions of vertical and horizontal in E kappa tau, in the sense that vertical is anything which is tangent to the fibers, and horizontal is anything which is orthogonal to the fibers. Also, the constant tau is something very well understood, and it is related. It is the so-called bundle curvature that measures the non-integrability of the horizontal distribution, in the sense that when tau is equal to 0, then the horizontal distribution is integrable and we get a product space. And when it is non-zero, then we get some more involved geometries. So, in this setting, Benoit Daniel in 2007 revealed the existence of a sister correspondence that extends Lawson's correspondence. In this case, I'm going to focus on the case of a conjugation. So if I fix a constant epsilon, which is just the sign of the -1, 0, or 1, then there is an isometric conjugation between minimal surfaces in one of the E kappa tau spaces with these parameters and constant curvature surfaces in this other space E epsilon 0, which is a product space. So here I'm interested in the case epsilon equals 1. Well, as I say, this is a particular case of a more general deformation, isometric deformation of H surfaces, in which the deformation is carried out in such a way that it also deforms the ambient space. It is the same as when as the associate family of the helicoid and the catenoid, but here when we deform the surface, we also change the space. And when I say conjugation, I mean that the parameter of the rotation, of the intrinsic rotation in the associate family is equal to pi over 2. So we will see in the next slide that this gives rise to very nice properties of the conjugation. Also, I would like to say that the Daniel conjugation is univocally determined up to isometries of both spaces which preserve both the global orientation of the ambient space and also the orientations of the fibers. This is, for instance, if here I have S2 cross R, in this second case, I cannot perform a mirror symmetry with respect to a horizontal slice, because in that case I reverse the orientation of the space and the orientation of the fibers. And this doesn't commute with the conjugation. In fact, if one looks at this picture, then we get the following cases for constructing an H surface in a product space. In the case of S2 cross R, if I want to produce a surface with positive constant mean curvature, I have to start with a minimal surface in a Berger sphere. And if I want to produce a minimal surface, I have to start again in S2 cross R. In fact, in this case, there is a notion of associated family of minimal surfaces in S2 cross R. In the case of H2 cross R, it's a bit more involved because there is a notion of critical mean curvature, which is H equal to 1/2. This is not related to the H equal to 1/2 I was mentioning in the previous video in S2 cross R. But this critical mean curvature, when the H is equal to 1/2, then the original minimal surface comes from Heisenberg group. For supercritical mean curvature, it comes from the Berger spheres, and for subcritical mean curvature, the corresponding minimal surface lives in the special linear group in H2 cross R itself, because here there is another notion of associated family. In fact, the differences in the geometries of H surfaces for different values of H can be more or less explained by the fact that their conjugate surfaces live in spaces with very different geometries. In fact, if epsilon is equal to 0, we recover the original Lawson's correspondence. We have that in R3 for H bigger than 0. Then we start in a Berger sphere, but in that case, the Berger sphere reduces to the rounded sphere of constant sectional curvature. In the case H equal to 0, we have the classical Weierstrass associated family of minimal surfaces in R3. So this is the global picture of correspondences and conjugation. So I would like to in this introductory video to explain a little bit more what is the geometry of an E kappa tau space. So on the one hand, we have a local model. This, for any kappa and tau, E kappa tau is locally isometric to this trimanifold, where omega kappa is some domain of R2 given by this inequality, and in this say cylinder model, because this is a disk times R, we plug this metric, this is explicit, and we obtain a trimanifold which is locally isometric to E kappa tau. Well, in this case, the geometry is very easy because the Killing submersion is just the projection over the two first components, and the unit Killing vector field is just the unit field in the direction of the third component, tangent to the fibers of the submersion. But it turns out that the model is not complete when kappa is equal to 0. In fact, this cannot be a projection into S2 when kappa is equal to 0, because this is a disk. And in fact, the geometry gets a little bit more involved. Then, to be precise, there is a global model in the case kappa bigger than 0 and tau different from 0. This is the case of Berger spheres. In that case, we consider the 3 sphere now inside C2. And we consider the Riemannian metric G given by this expression, where these brackets represent the round metric in S3, and psi is this vector field proportional to the position vector. So in that case, this is a global model for the Berger spheres. We can see that when kappa is equal to 4 tau squared, then this vanishes and we just get some metric proportional to the round metric. And then we get the round spheres, as I was saying in the previous slide. So in that case, the Killing submersion is nothing but the Hopf vibration, and it is given in this model by this expression. And well, we can plug the local model into this global model by just doing this local isometry. So this is I will not do any computation throughout the talk, but computations can be done by using these local coordinates. In fact, I will be more interested in geodesics, and in any Kappa-Tau space, a geodesic curve projects to a curve of constant curvature in the base M2 cross R via the Killing submersion, and also makes a constant angle with the Killing direction. This makes very easy to compute all the geodesics in any of the E Kappa-Tau spaces, and we obtain that there are three possible geodesics, say different kind of geodesics. On the one hand, we have the vertical geodesics. I will draw them in blue all the time, and they are the fibers of the submersion. Also, I will have horizontal geodesics that project into a curve of constant zero curvature of the base. That this is a horizontal, a geodesic of the base surface, M2 kappa. And then we have the geodesics that are neither vertical nor horizontal. I will call them oblique geodesics, and they project onto a curve of non-zero constant curvature of the base. So I have some kind of tilted helices in this picture. It is very interesting to point out that there are axial symmetries in all Kappa-Tau spaces about any horizontal or vertical geodesic. So this is one of the tools I needed in the Lawson's correspondence, as I explained before, and this is something that it is okay in these spaces. If tau is equal to 0, then we also have vertical planes. So tau equal to 0 means that it is a product space. So we have a vertical plane, which is the product of a geodesic of the base times the real line, and horizontal slice, which is just the base times a point in the real line. And in that case, we have mirror symmetries about horizontal and vertical planes. So these are the isometries I will need in my constructions. Well, just to finish the generalities of the conjugation, I will try to explain how to use the isometries and the geodesic components of the boundary to produce complete H surfaces in any product space. I here have written H2 cross R and S2 cross R, but well, this is also okay and reduces the classical setting in R3. So if we take two conjugate surfaces, a minimal surface in the Berger sphere and or in any other Kappa-Tau space, and the corresponding H surface in the product space, both of them are isometric. This means that they are isometric immersions of the same Riemannian surface into the two spaces. One is minimal, the other one has constant mean curvature, and their angle function, which is the angle, the cosine of the angle that the normal vector field makes with respect to the vertical Killing direction, is the same at corresponding points of both surfaces. Also, in computations, it's sometimes useful to use that the tangent part of the Killing vector field and also the shape operator rotate 90 degrees in sigma with respect to sigma tilde. Well, this is to say that the geometry is somehow rotated, and it is also equivalent to say that vertical things become horizontal and horizontal things become vertical. So I will restrict to the boundary behavior, as in the Lawson setting, that when we have a horizontal geodesic in the original minimal surface, then it corresponds to a planar line of symmetry into the H surface. This is, you can see this picture here, that if we have a horizontal geodesic, then in the initial surface, then it becomes a planar line of symmetry contained in a vertical plane in the corresponding surface. Also here, I have highlighted that the horizontal projection has length the integral of the angle function, and the vertical projection has length the integral of square root of 1 minus the angle function square. Well, one has to be careful here because this is some kind of signed length, in the sense that here the angle function could be positive or negative, and also this guy could be positive or negative, though I have written it positive here. So one has to be careful and look for points where nu is equal to 0 or nu is equal to plus or minus 1 to see if this curve goes up or down and to the left or to the right. Likewise, we can do the same for vertical geodesics, and a vertical geodesic contained into the initial surface become a plane line of symmetry of the second surface lying in a horizontal plane. Also, in this case, it is much more difficult to control this conjugate curve because the only thing we know is that its geodesic curvature is related to the angle of rotation of the normal along the original curve. And the relation is that the geodesic curvature of this curve as a curve of the horizontal plane is 2h minus the rotation speed of the original normal field. So, well, this is okay, this is a very nice formula, but in the case of H2 cross R or S2 cross R, the geodesic curvature is not as strong as in R3 because the geodesic curvature doesn't reflect the rotation of the normal of this curve because we have some curvature in the base. So, the original surface, if it is bounded by vertical and horizontal geodesics, then it can be extended to a complete minimal surface by axial symmetries. And the corresponding surface, the H surface, can be extended in that case by mirror symmetry about the vertical planes and horizontal planes in which its boundary is contained. So we just have to ensure that our initial surface is bounded by some geodesic polygon consisting of vertical and horizontal geodesics. Here I have one easy example, which is the case of minimal helicoids, the spherical helicoids in Berger spheres. So in Berger spheres, we have a notion of helicoid in which we take a horizontal geodesic and we rotate and translate it along a vertical geodesic. So it doesn't matter what is the rotation speed, this surface is always minimal. So we can see that helicoids are always minimal in spheres, but the conjugate surfaces, and I like to say that this example is surprising because depending on the rotation speed here, that is something like very naive in the case of Berger spheres, we get spheres, rotational invariant spheres, nodoids, cylinders, or unduloids, cylinders, or nodoids in R3, S2 cross R, and H2 cross R that even though they are rotational invariant, they look very different. And it is related to the direction of rotation of the helicoid in the Berger sphere. Okay, so these are the vertical Delaunay surfaces. They are rotational invariant. Now, in the next talk, I will be interested in constructing these examples in an horizontal direction. And this cannot be done by, for instance, solving the ODE in which we have when we impose the condition of rotational invariance. So we shall see how to use the correspondence to deal with that more involved construction.